of about 4%, so it's got a reliability of about 96%. Second one has a p-bar of 0.053, about 5%, so it's got a reliability of about 95. So you got a pretty good process here, 94, 95% reliable going through the process. So given these kinds of charts, you need to make sure you know how to translate these into reliability data that management is interested in. So you might take the path of the binomial distribution of predicting the number of defectives you'll find in given sample sizes, or management might want to start talking about what's the overall reliability of our process. We've got these two branches of quality engineering that take place within the story. So I'm going to switch the spreadsheet here. Wrong spreadsheet. So here's that first chart. Just in Excel, same chart you're looking at. Here's the second one. Okay. So the question would be, what kind of math can we do with that? I'll blow this up so you can see it. Hope you can see it. There's three solutions here. You might be asked, what will be the frequent reliability of these two steps operating in series? Step 1 followed by step 2. If it's a series system, we have to do some basic math. So we take the data right off the control charts, upper limit, center line, lower limit. For each, we subtract from 1 to get the worst reliability from the upper limit, the expected reliability from the center line, and the best reliability from the lower limit. Notice how they swap. The upper limit on the P chart is your worst case. Okay, the lower limit in your reliability is your best case. So for all three solutions, it's very similar math for these two lines. I've translated the control chart data into the reliability data right here. And as I always say on exams, show your work. Okay? So given that, then the math to calculate series is a little different. How do I calculate a series probability? I take the probability, I multiply these two reliabilities together. It's a series. Reliability in series goes down. Remember that. So if you use the wrong formula mistakenly, which is common, you're okay as long as you double check your work. If it's series, make sure the number went down. If it didn't go down, you used the wrong formula. That's why I keep stressing that. This happens to be the formula of the product of those two numbers. Hopefully you'll simply remember that and you'll get it right. But you'll know you're right if the answer you get is smaller than either of the numbers you were given. Series goes down. So I must have used the right formula because I got a smaller number. And I do that multiplication in each column. This display simply converts that decimal into a percentage. So I'm displaying the reliability as a decimal, and I'm displaying it here as a percentage. So the series 3-point reliability for those processes is roughly 91%, ranging from 84% to 97%. Pretty reliable. But think about that on a day-to-day basis if you're part of a complex process. The day the process is running at 97, that's a good day. But the day it's running down toward 84, that's not so good. Okay, so your worst case reliability sometimes, what you really want to pay attention to is a quality engineer. That's where you jump back to your binomial distribution. How often, what's the probability I'll be running down here? Because to have worst case, both of those steps have to be having their worst case. If it starts to sound a little like discrete simulation, it starts to sound a little like OR. It should. That's the skill you use here. Because we can calculate the probability of 10 defects in the first process. But what's the probability of the first process having a lot of defects at the same time that the second one has a lot of defects? That's not as common as you think. I shouldn't actually get this 84% that often, because both of these processes would have to be having a bad day for that to happen. And I can run a discrete simulation through the binomial distribution to figure out how often that's likely to happen. So if one day in 10, either process is likely to have a bad day, what's the probability that those two processes will both have their bad day on the same day? Maybe it's one day in 80. So every few months, I'm going to have a really bad day. But I want to know that. I want to be able to tell management, predict that to management. It's amazing how well these charts and these formulas predict real-world behaviors. Like I said, NASA predicted the Columbia disaster in 2003 to the exact flight in 1989. These formulas are deadly accurate in terms of making their predictions. I don't know why the binary distribution describes the real world. I don't know why the Poisson distribution, I don't know why the Z-curve describes the real world. But it does. And it works, and we trust it, and we use it as engineers all the time. So if the exam question says, give me the 3-point reliability for each process in series, you're going to do this version of the solution. If the exam says, give me the solution in parallel, you're going to do the one here in the middle. Again, the control chart reliability is the same data. Okay. But in this case, my parallel reliability is a different formula. Okay. It's the formula for reliability, which is 1 minus the product of both steps failed. Okay. So again, hopefully you'll get the right formula and you'll give me the correct answer. But check your work. If the parallel process, the reliability goes up, not down. If you get a lower number here, you did something wrong. Certain things are easy to check. It's like on the probability on the first exam. Those of you who got 139% defect rate could have caught that, because you can't have 139% defect rate. Know the simple rules, and you'll catch some of your biggest blunders. So parallel, it goes up. These are the answers for the parallel application. So if these two steps are in parallel, and they were already pretty good, they get great. In parallel, they would perform at 99.8%, varying only as low as 99.3%. It's a great parallel process. If the question asks you how the two processes would do where the second step is a backup for the first, you've got this solution. Which, as I said before, when there's only two steps, you're going to get the same answer as you had for the parallel. But learn both formulas, because they will not give you the same answer if it's a 3-step parallel process with a double backup. You get a different answer. They both increase the probability, but for different reasons. Okay? So in backup, you've got a different formula. You basically do the math for each and get your ratio. So this is a good process if it's running in series. It's a pretty great process running in parallel backup. Now the probabilities for parallel and backup are the same. This is a potential short essay question. Just a potential that I can count on. If the parallel and backup give you the same probability, what are the circumstances under which you as an engineer would recommend one over the other in your design? We started hinting at that the other day, but I want to spend a few more minutes on it since I did ask this kind of question. Okay, I get the same reliability, parallel and backup. Okay. So I don't expect a short answer to be exhaustive, but I want you to think like engineers. Parallel has certain advantages. An advantage to parallel is you don't have a cutover time. Okay, when you have a backup system running, even if it's a very small amount of time, it takes time for the backup to kick on when the primary fails. So if you've got critical function, it's hard to replace. Okay? Parallel is often better. Back in the early 1970s, mid to late 1970s, we were doing space shuttle navigation software in the shuttle industry. The shuttle navigation system was targeted in its initial design to be a primary backup system. Okay, and then they went to a primary with parallel on the backup. So if the onboard navigation computers failed on the space shuttle during a launch, they wanted to be able to go to a backup to make sure they had complete reliability on guiding this thing. Because rockets, as you know, are inherently disastrous in terms of ready, fire, aim. And we often learn ready, aim, fire as kids, but aeronautics is really ready, fire, aim. You get the rocket ready, you light it and shoot it into the sky, and the entire time it's flying, you're trying to control it into its attitude. You don't aim a rocket, you can't aim a rocket until it's already flying. So ready, fire, aim. So the whole time navigation software is trying to figure out the very infinitesimal levels where this flight pattern is. And it turned out when they started simulating and building the software for the space shuttle, that a backup system might only take 5 to 8 milliseconds to kick in. Okay. But at Mach 34, the ship was in trouble in that kind of span of time. That was too long to use a backup system for space shuttle navigation. So the actual space shuttle navigation is a 4-way, 4-vote parallel system. 4 different computer systems are run simultaneously, solving the navigation problem for adjustment of the ship. They all vote. As long as 3 of the 4 come up with the same answer to about 12 decimal places, the ship does what the navigation system says. So they basically built a system where all the systems had to run. Now, to avoid one of the risks of going parallel is that the parallel. What if your backup in the second parallel system fails for the same reason as the primary? What you don't want, if you want a 4-vote navigation software system for a high value asset, whether it's a space shuttle or a Patriot missile, we have the same problem in missile technology. You don't want to design your navigation software and put it on 4 different chips and put them in parallel in the device. Because what if the failure is caused by a design flaw in the chip? All 4 chips are going to be wrong. Or what if the chips tend to wear out for similar reasons? They're going to your parallels are going to burn out and wear out at the same time as your primary. It turns out your parallels are useless unless they vary enough that they have a different failure profile. Not necessarily higher or more reliability. It's fine to have one chip that will fail at one stuff and something else that fails goes to something else. They won't fail on the same element. That's why you go to the 4 votes. But it was important when they built the space shuttle to have 4 parallel navigation systems. But they had to make sure that when one of them was wrong, it was uniquely wrong. 4 different contractors got the contract to create navigation software for the shuttle, all working to the same master specs, but they weren't allowed to talk to each other. One of the 4 was developed by the company I worked for at the time, Exxon, in Florham Park, New Jersey. So we designed and built a navigation computer for the space shuttle. Knowing it was only one of 4, we have no idea how the other 3 were created. But we all had to meet the same spec for giving the same answers to the same problem. So as long as we all came up with the same answer within 12 decimal places of each other, the shuttle did whatever our software said. And that's how they avoided the failure. So one system could fail for any number of reasons. The chances that any of the other 3 would fail were infinitesimally small according to the binomial distribution because of the design patterns and reliabilities. So none of the systems was foolproof, but the odds of 2 of them failing at the same time on the same calculation were infinitesimally small. So parallel systems could be a challenge that way, precisely because you don't want the parallel systems to fail at the same time as the primary. It's not having a parallel. Translate that now into backup thinking. Why would you do a backup? So you've got the problem of delay. So backup presumes you can get to your backup fast enough, the time gap in between isn't critical. So backups have a certain advantage. They're typically not running while the primary is running. So I don't have the problem of creating 2 parallel, completely different designs, which is very expensive. I can make the backup an exact copy of the primary. I wouldn't run that as a parallel, because if the primary will fail in 6 months, and I run the backup in parallel, it's going to fail in 6 months. At the very moment I need the backup, it's going to fail because it fails just like the primary. But I know it's good for 6 months, so as long as I don't turn it on until I need it, when the primary fails, it's going to run. So one of the advantages to running a backup is it can be an exact copy of the original, and it probably won't fail when it's needed. Another common way we tend to use backups is often the backup system is the prior generation of the primary. We take out the primary computer, but we keep it, make it a backup, and put a new computer in. The backup is often the -1 generation of whatever we're using. So it's not as good as what we're using, but I know it does the job. We used it for years, and it had a backup that I've now retired. So I gradually retire things by making them the backups. And the -1 system, I always know will serve as a useful backup because it was our primary for years.